Okay, Unit 1 review video. We reviewed trig, we learned about limits, asymptotes, and continuity. I'm not going to review trig with you. If you need to review trig, you need to go to the Unit 1, Lesson 1 video. Okay, but let's go ahead and start reviewing limits. Okay, here's just a graphical example of some questions about limits that we can ask. Now, for the most part, let's say like here, I got this point, -3, 3. For the most part, I can see that f of -3 equals 3. Limits is what's going to happen as we approach this x value -3. I would write like the limit as x approaches -3, and then you could either say from the left or from the right. And this is like f of x. Well, if I go to the left of -3, I see I'm very close to this point 3. If I go to the right of -3, I'm very, very close to this point 3. So this is a situation that is typical for functions that are continuous. Limits and function values agree with each other. We'll talk about how this is like the definition of continuity. This function is continuous at -3, and the limit's equal to 3, and the function value is equal to 3. Cool. But most of the questions concerning limits do not deal with the simple situation. Instead, it deals with these situations where limits and function values maybe disagree. So we're going to focus our attention at -4, at 1, and at 6. Let's start at 1. X equals 1. Okay, well, f of 1, so the function value defined at 1 would be this closed circle 4. Okay, cool. Now let's look at the limits. If I looked at the limit as x approaches 1 from the left, I'm going to go to the left of 1. Just to the left of 1, my function values are up here. And as we're getting closer and closer to 1, the y values are getting closer and closer to 4. So the left-hand limit and the function value agree. If I look at the right-hand limit, just to the right of 1, my function values are down here now. It's just directly below or directly above. Down here, as I get closer and closer to 1 from the right, my y values are getting closer and closer to -2. Because the left-hand limit, we call this the left-hand limit, and the right-hand limit do not agree, we will say the limit as x approaches 1 in general does not exist. Okay? And since the limit doesn't exist, the function is not continuous, even though we do have a function value. Let's look at x equals -4. In this case, I do not have a defined function value. F of -4 is undefined. If I look at the left-hand limit, though, so to the left of -4, I'm approaching this y-coordinate of 2. If I look at the right-hand limit, so this approaches -4 from the right, my function values are here, are also approaching the value of 2. Now, it doesn't matter that this is an open circle. It's that we are approaching the location. It's almost like we don't care what's going on right at this location because I'm looking just to the left and just to the right, and I see my values are getting closer and closer to 2. That means the limit in general as x approaches -4 is 2. Even though we don't have a function value, limits don't care about what's going on at the value. It just cares about what's going on to the left and to the right of the value. Okay, so function value is undefined, but the limit does exist. Let's look at x equals 6. Here, I do have a function value, but the closed circle is at 2. So f of 6 is 2. However, my function values to the left and to the right of 6 are not around 2. They're up here and here, which are very, very close to 5. So the limit ends up being 5, even though the function value is 2. Okay? So that was an introduction to limits. Some other questions that concern limits are this type of function. We need to recall this function. Remember, if x is greater than 0, we're going to have x over x, which is 1. But if x is less than 0, I'm going to have a positive x because of the absolute value, but then a negative x because of there's no absolute value down here, which is -1. We need to be comfortable with a type of function like this looking like this. It's called the jump function. It's jumping from -1 to 1. If I'm asking you the limit as x approaches 0 from the left to the left of 0, I'm down here at -1. Now be careful, if I put like another value like a 2 here, well then all of a sudden this would change into a 2 and this would change into 2, and I wouldn't be jumping from -1 to 1, I'd be jumping from 1/2 to -1/2, like that. If I put like a 5 here, then all of a sudden it would be jumping from 5/2 to 5/2. If this was a shift, all of a sudden I make this an x minus 2, and this an x minus 2, well then I would just shift my graph. Let's see if I can ungroup this. Where I would be jumping at x equals 2. So I would be going up to 1/2 at 2 and -1/2 to the left of 2. Okay, so that's the jump function, remember that. Also, reminder about piecewise functions. So piecewise functions, we're using this piece for x is less than 2, we're using this piece for x is greater than or equal to 2. So you really don't have to sketch if you don't want to. You're asked to find the limit as x approaches 2. Well, if I'm to the left of 2, I would be using 3 minus x. So the limit as x approaches 2 from the left is just going to be this function with 2 plugged in. And I get 1. So I say that the left-hand limit is 1. And then if it's x is greater than or equal to 2, I'm going to be using x squared minus 6. So if I'm looking at the limit as x approaches 2 from the right, I'm just going to plug in 2 into this one. I get 4 minus 6, which is -2. The right-hand limit is -2. These do not equal each other. Therefore, this limit as x approaches 2 in general does not exist. Now you might be thinking, oh, okay, so the limit doesn't exist for this function. It's like, no. It's just at 2. So if you were to sketch this, and you could sketch this, you would see that the two pieces don't meet up. The two pieces are not continuous at 2. We got 3 minus x, which stops at 1, and then we got x squared minus 6, which will start at -2. So we don't meet up. The limit doesn't exist at 2. But if I ask you what's the limit as x approaches 1, you don't say it doesn't exist. You're not going to plug in 1 into both of these because you are only using this piece when x is 1. So I realize, oh, okay, for x is less than 2, I'm going to use 3 minus x. So this limit is just going to be the same as the limit as x approaches 1 of 3 minus x. We would just be able to plug in 1 and get this was 2. That would be my answer, and you would be able to visually see, there's my limit there, 2. Okay, so be careful with piecewise functions. You don't have to plug into both all the time. It's all about which piece should we use, or are we at a location where we need to use both pieces. Asymptotes, horizontal asymptotes. If you think about horizontal asymptotes, it's what is going on all the way to the left and all the way to the right of the graph. Are we approaching a value? Are we approaching 0? Are we going down to -infinity, positive infinity? That's the key when you are asked to find horizontal asymptotes. So if you're asked to find the horizontal asymptotes, you would look at the limit as x approaches positive infinity and the limit as x approaches -infinity. Now, when we are plugging in big values into functions, let me just plop this sucker down. Plugging in large values, it's all about growths. The fastest growing dictates what happens to the function. We talked about when we did this lesson, if I'm plugging in very large values, even though I have x to the 10th, 2 to the x is going to grow faster than x to the 10th. So if I plug in larger and larger and larger values into 2 to the x, this will be so much larger than this that this is like adding a very, very small decimal to a very, very large number. This will be insignificant. I can cross it off. Even though you see like 4,000, well, 4,000 is a no growth number. This is going to be growing. This will eventually be like adding a very, very small decimal to a very, very large number. So I got 2 to the x over negative 3x to the 80th. If I plug in infinity, this will be growing faster than this. If I think about faster growth over slower growth, think about like 1 over 1. Let's say I'm growing the numerator of this fraction faster than the denominator. Well, let's say multiply by 10 versus adding 1. Multiply by 10 versus adding 1. Multiply by 10 versus adding 1. There's faster growth over slower growth. What's happening to these fractions? I got 1, 5, 33, 250. These fractions are growing. We'd be approaching infinity. But be careful. See this negative 3? We actually have a negative in the denominator. Because we have a negative in the denominator, I'd actually be approaching negative infinity. So careful with signs of infinities. Now, same thing, I'm plugging in negative infinity. Be careful with exponents. 2 to the negative infinity is like 1 over 2 to the infinity. That's actually 0. 2 to the x or any exponential functions, if you plug in negative values, are actually no growth functions. So I actually would cross off 2 to the x in this situation. I'd cross off 4,000 again. But then I have 5x to the 10th over negative 3x to the 80th. This is our faster growing function compared to the 2. If you think about faster in the denominator versus slower in the numerator, start with 1 over 1, 10, 100, 1,000, 2, 3, 4. These decimals are 1, then 0.2, then 0.03, then 0.004. These fractions are getting closer and closer and closer to 0. Okay, let's look at this guy. Limit as x approaches positive infinity. Limit as x approaches negative infinity. We've already talked about how we could get 0 or plus or minus infinity. Let me just get rid of this guy. If I'm plugging in infinity in the numerator, 2x to the 4th, gone. E to the x is growing faster. 4x to the 4th, gone. E to the x is growing faster. Well, now I have a situation where I have 3 e to the x over negative e to the x. Well, the growths of the e to the x would actually cancel out, and I'd have a value that we'd be approaching, negative 3. Okay, so to the right, I'm approaching negative 3. Here's my first horizontal asymptote. But to find the horizontal asymptotes, make sure you look in both directions. Because if I look towards negative infinity, all of a sudden, e to the x's, as x approaches negative infinity, is going to approach 0. So this is like gone. This is a no growth function. This is a no growth function. I'd end up with 2x to the 4th over 4x to the 4th. These would cancel. I end up with another horizontal asymptote at 1/2. You will see lots of questions on horizontal asymptotes on your midterm. I just put it together, and I was surprised how many popped up. So be ready for horizontal asymptotes. Be careful. Here's a good question. Cosine of 1 over x. If I plug in infinity, it ends up as cosine of 1 over infinity, which is the same as like cosine of 0. Well, the cosine of 0 is 1. Very similar to e to the 1 over x. That'd be like e to the 1 over infinity, which is the same as e to the 0. 1 over infinity would be approaching 0, and e to the 0 is 1. If you have a square root, now you would think, okay, the 3 is gone, the 5x is gone compared to the x and the x squared. But then I'd have 2x over root 9x squared. Let me just 2x over root 9x squared. Now the root 9x squared can simplify to be 3x, but you got to be careful. when we have this square root of this x squared, we're really thinking that, the signs are not necessarily positive. It could be positive or negative. I'm going to leave a question mark there. Now the x's will cancel, so I got the answer of 2/3. And the truth is, in one direction I'm going to get positive 2/3, in the other direction I'm going to get negative 2/3. If I go back to my original equation and plug in a negative value, I know the numerator is going to be negative, but the denominator is going to be a positive because it's like a negative value squared. That's a positive times 9 is positive. Square rooted stays positive. Square root of a positive number is a positive number. It's when we're solving equations that we will have the plus or minus. So I'm really doing this just to make sure you know that it could be positive or negative. In this situation, my answer is negative 2/3. Trig functions, remember trig functions do not have any growth. It's just going to oscillate. It's going to go up and down and up and down and up and down versus x will grow. So this is going up. So we're talking about no growth over faster growth. This is approaching 0. Okay, think of sine x as a constant as x approaches infinity. Vertical asymptotes, you don't see these that often, but just to remind you of how to handle them, we're plugging in a value, -2, that if I plugged it into the original equation, I'd get 5/0. This is an indication that I have an asymptote. Okay, now how do I figure out what's going on? We don't say this does not exist because we want to pick the direction at which we are heading towards this asymptote at -2, if I'm trending up to the left or trending down to the left. Positive infinity or negative infinity is the answer that we're trying to look for. Well, what I recommend is on a number line, first identifying what is to the left of -2. It's like -2.001, understanding that, 0 is to the right of -2. I take that value and I square it. I know that value is going to be a little bit bigger than 4. I don't really care what exactly it is. I'm just going to write it as 4.001 because this value times itself, boom. If I subtract 4 from 4.001, I'm going to get a number very, very close to 0, but it's going to be a positive. If I have a number divided by something very, very infinitely small and positive, this is going to be infinitely large and positive. So this would be approaching positive infinity to the left of -2. Here they're asking you about the limit as x approaches 4 in general. We would look in both directions. Make sure if you're looking at a limit, you need to look at the left-hand limit and the right-hand limit. -4 from the left, -4.001. This will end up being 0.001 squared. It'd be a positive 0.001. So left-hand limit would end up being -5 over something very, very close to 0 but positive. So this will be negative infinity. The right-hand limit, I plug in something like -3.009. I subtract that from 4, that's close to 0 but negative. But when I square it, it'll turn into close to 0 and positive. So all of a sudden, this is also negative infinity. Even if you're working with infinities, if the left-hand limit and the right-hand limit approaching the same value, you can answer this as negative infinity. You could say it does not exist as well because of the vertical asymptote, but just heads up in case you see something like that. All right, so that's asymptotes. Now moving on to being continuous. Definition of continuity. Something is continuous if limits equal function values. We usually say the limit as x approaches c of f of x equals f of c. This is typical. Limits equal function values for most of the functions that we look at. X squared, every single point of x squared is continuous because the limits equal function values. It's when we have a discontinuity, that's when we are not continuous. Types of discontinuities, if we remember, we could have a jump. Here the limit does not exist. We could have a hole. This is considered a removable discontinuity. We do not have a function value there, but we do have a limit. And then we have asymptotes. This would be considered an infinite discontinuity. This is non-removable. This is also non-removable. We will focus our attention on removable discontinuities and finding locations of them. To find a location of a removable discontinuity, first we realize that a removable discontinuity will occur typically when your f of c value is 0 over 0. So if I plug in c, I'm going to get 0 over 0. These are usually piecewise functions where we'll have jumps, or this jump function, so be ready for that. Infinite discontinuities are when we typically plug in a value and we get a number divided by 0, indicating we're going to be approaching infinities. 0 over 0 typically will approach a value, like any numeric value. Now, to find a location of removable discontinuity, we're going to find that if we simplify things, we'll be able to see the removable versus non-removable discontinuities, and then we'll be able to find the location of the removable discontinuities. This is x minus 5x plus 3. I realized that f of 5 would give me a number over 0. That's an indication that I have a non-removable infinite discontinuity. So I'm going to have an asymptote on this function at 5. But if I plug in negative 3, I'm going to get 0 over 0. That is the location of a removable. That means, like, we could find the limits as x approaches negative 3 of this function. We would not have a function value. F of negative 3 is undefined, which means the function value doesn't exist, but we can find the location. To find the location, we can simplify and remove the removable discontinuity, then plug in the value, and we get negative 1/8. Okay? So just be ready to simplify, to plug in, to remove the discontinuity. We'll do another question like that. For a piecewise function, we can find a value that ensures continuity. For piecewise functions, what we're worried about is whether or not the pieces meet up at a location. So I would make sure that this first little piece meets up with the second little piece at 5. I'd get 25 minus c for my first piece equals 20 plus 2c for the second piece, and then I'd solve for c. Subtract 20, add c, divide by 3. Now, this was a piecewise function. We call this a pointwise function. For pointwise functions, it looks like this is going to be used for every single point except for 3. Okay? This point will plug in what's going on at 3. Now, if I found, we'll call this like g sub 1. G sub 1 at 3, I would know what this is equal to. Well, if I plug in 3, I realize that I get 0 over 0. That means this majority of the function has a removable discontinuity at 3. Well, that means I need to find the location of the removable discontinuity, or the limit of this. I could factor. It's x minus 1, x minus 3. Remove the removable discontinuity, plug in 3, I get the location is 2. That means this point, g sub 2, at 3 must equal the limit, which is 2. So 3x plus b has to equal 2 when x is 3. So 9 plus b has to equal 2. B has to equal negative 7. We'll call the intermediate value theorem. It deals with functions that are continuous. So we must say that this is our continuity theorem. It says if we have 2 points here and here, no matter how we connect it, as long as we're connecting it in a continuous way, we're going to pass through every single one of these y values at least one location, no matter what. What we do with this theorem is we show that like certain solutions exist. Like show that this function has a solution to f of x equals 5. Now, if I asked you like, hey, show me that this could equal 5, you would try to solve this by hand and you'd go nowhere fast. But instead, if you realize, okay, this is continuous, it doesn't have a denominator that equals 0 anywhere. It's got 2 points. F of 1 is 4 minus 6 plus 3 minus 2, which is negative 2 plus 1, which is negative 1. And then f of 2 is 4 times 2 cubed. That's 4 times 8. 32 minus 24 plus 6 minus 2 is 12. So just knowing that the function is continuous and knowing I have these 2 points, 1, -1, and 2, 12, I know I'm going to have to pass through 5 somewhere for some x. The solution must exist. What it is, I don't know, but I know it's somewhere between 1 and 2. Okay, that was Unit 1. A little bit longer than probably the rest of the videos because we haven't really talked about this stuff much from unit to unit. It's kind of stuff that we learned and then we moved on from. So make sure you review Unit 1.